Alright. So again, I'm assuming you have the problem in front of you. We're now doing part B. The first part of part B asks us to determine the distance from the left, the center of mass of the system. Using the equation that R, or position, of the center of mass equals the summation of mass, position, over mass, we get, this equals original mass over here times 0 because it's right on the left, plus 2m over here where it will be directly after the collision times length L over 3m, which equals 2/3 L. Now it asks us to indicate the direction of the center of mass on the picture. Since we know that the center of mass is 2/3 L, we can say that it's about right here. And since the center of mass will go in the same direction as the initial velocity with no added force, we know that the center of mass is going to go in this direction. V final. We are now asked to determine the speed of the center of mass directly after the collision. Since this is not attached to any fixed point, we can say the linear translational momentum will be conserved. So mv naught equals 3m, because the mass of the system is now m plus m plus m. V final. And again, V final equals 1/3 V initial. Now we are asked to determine the angular speed of the system immediately after the collision. To do this, we use the conservation of momentum that says angular momentum initial equals angular momentum final. Angular momentum in this case equals mass times velocity times sine theta r. We know that r, since it's the distance the object strikes the system, r is going to be 1/3 L. Since it's striking perpendicular, sine theta is 1. We'll leave that out. So it's mass times velocity initial equals 1/3 L equals L initial. L final equals I total omega. I, because it is the sum of 2 point masses, we get I equals 2/3 L squared, since it's the distance from here to here for one mass, m, plus 1/3 L squared 2m. Because over here, we get the 2 m's concentrated at one point. Now, we set these two equations equal to each other. MV, Bill, shut up. MV, hey.
That's on record too. We could report you for.
Don't interrupt our video.
We have to do this again. We have to do this again.
No, we don't. We can cut this out. MV.
Except I don't think I want to.
Sucks.
Okay.
MV not 1/3 L equals. We're going to square the 2/3 and the 1/3 now. 4/9 L squared plus L squared m plus 1/9 L squared 2 2m times the quantity omega. We can now add the fractions inside these parentheses to get 2/3 L squared m omega. Now the equals mv naught 1/3 L. We now solve for omega. mv naught 1/3 L over L squared m 2/3. So we can cross out these 3's, cross out this L, cross out the m's, and this equals omega, which equals m, no, there's no m, never mind, v naught over 2L. Boxed answer. The last part of the equation asks us to determine the total change in kinetic energy of the system. We know that energy final minus energy initial is the change in energy of the system. So we get energy final is 1/2 mass of the system, V final squared, which we said earlier to be 1/3 VO, 1/9 V squared plus 1/2 I, which we have over here, said to be 2/3 LM, which we summed over here, omega squared, which we said to be VO over 2L. So we get V naught squared over 4L squared.
Evan,
Minus the original energy, which again is 1/2 mv naught squared. And that equals our change. So first things first, we need to add up these two parts. So we get 1/6 mv squared plus I we know is 2/3 L squared m. We can cross out these two L's. Cross out these 2's. 1/12 V naught squared m. That's in the wrong order, but that's the order I saw it in. Minus 1/2 mvo squared. So this totals 1/4 mv naught squared minus 1/2 mv naught squared, and that equals negative 1/4 mv naught squared. And that's the change in energy of the system. And we're done.